have the sum and difference shortcut. First thing you want to do is, this is a quick representation of it. A, which is the amplitude, this is what you want to do with A. You get the leading coefficient of sine and cosine. You would do it n1 squared plus n2 squared. That gives you your amplitude. To find data, you have to do tan -1 or arctan which is on the calculator, cosine over sine. And after you get your answer from this, you have to divide by pi. And this is the easiest way to find out sum and difference questions. The shortcut gets you easy answers and easy solutions. Right here is the shortcut. And always don't forget to divide by pi. This is essential. All right. Stop recording. Now we have reciprocal identities. Reciprocal identities are useful for when we have questions where we're trying to simplify the equation to a single cosine or sine function. The reciprocal identities basically make it easy to simplify equations, meaning that if you have cosecant, you can make it 1 over, which equals 1 over sine, meaning that's a reciprocal of cosecant. And secant, 1 over cosine, and cosine would be 1 over secant, and vice versa, sine would be 1 over cosecant. Tangent and cotangent also play into this. It's not so much a reciprocal, but it's an easy way to simplify it. You get sine over cosine and cosine over sine. I'm going to show you a reciprocal identities example problem. You have cosecant theta times tangent of theta over secant of theta, and that is subtracted by cotangent of theta. First, you want to change into their sine and cosine reciprocal identities. For cosecant, you want to do 1 over sine theta times sine theta over cosine of theta, and that's the tangent version. And then all over 1 over cosine theta. And then you want to subtract that by cosine of theta minus sine theta. First, you can see this clearly simplifies to 1 sine times cosine gets you 1 cosine of theta. And on the bottom, that would make it 1 over cosine of theta over 1 over cosine theta. And that just equals 1. And then you have to do the minus cotangent. And so you just have 1 minus cotangent of theta. That is your final answer. So now we have the initial sum and difference formulas for sine and cosine. For sine, it will be sine, imagine it would be sine A plus B. This would equal out to sine A cosine B plus sine B cosine A. And for sine A minus B, that will equal sine A cosine B, and then minus cosine A sine B. For cosine, it's just a little bit different, a little trick. It's not sine A cosine B, it would be cosine A cosine B, not plus, it would be minus sine A sine B. And one more, cosine A minus B, that will equal cosine A, cosine B, plus sine A, sine B. Okay, now we have, imagine we have sine 75 degrees. To get this into our sum and difference formulas, you want to do sine 45 plus 30. Now we have our A plus B. So now it would be sine 45 degrees cosine 30 degrees plus cosine 45 degrees sine 30 degrees. Sine 45 degrees, we just simplify down to root 2 over 2, and cosine 30 degrees, we just simplify down to root 3 over 2. So now we have root 2 over 2 times root 3 over 2 plus root 2 over 2 times 1/2. Since sine 30 degrees just equals 1/2. This will get you root 6 over 4 plus root 2 over 4, and that gets you your final answer of root 6 plus root 2 over 4. Cofunction identities are trig relationships that connect the function of an angle to its cofunction of the complementary angle. So right here we have sine x plus pi over 2. That would just change the cosine of x. And negative sine x minus pi over 2 also would change the cosine of x. But if you have sine negative x plus pi over 2, that would also change the cosine of x. And then on the other hand, if you have cosine x minus pi over 2, it would equal sine of x, because it's an even function. If you have cosine negative x plus pi over 2, it will be sine of x. And for cotangent and tangent, if you have tangent pi over 2 minus x, that would equal cotangent of x. But if you have cotangent pi over 2 minus x, that would also equal tan of x. Now we have transformations for sine, cosine, secant, or cosecant graphs. For all of these, the period would always be 2 pi, no matter what. But the only time it would change is if there's a number in front of the x. Think about it like this. If you have 4x, what you would do is, in this case, 4 is a shrink. So it would be 2 over 1 times 1 over 4, and that would make it 2 pi over 4, and that would mean the period is now only pi over 2, cutting in half. For horizontal reflections, this affects the 5 holy tick marks. So say the horizontal reflection is now, let's say it's now, it moves pi over 2 to the right. The 5 holy tick marks, which are 0, pi over 2, pi, 3 pi over 2, and 2 pi, would all just move right to pi over 2. So 0 would now become pi over 2. Pi over 2 would now become pi. Pi would now become 3 pi over 2. Sorry. Yeah, it would become 3 pi over 2. 3 pi over 2 would now become 2 pi. And 2 pi over 2. Or 2 pi would just become 5 pi over 2. And there is really no change for horizontal, vertical translations. If you go up 1, it would just seem the range would follow. Since the range is always -1, 1, it will now change to, if it went up 1, it would be 0, 2. Or if it went down, it would be -2, 0. Terminal points. It kind of is the foundation of trigonometry because it connects angles to coordinates in a simple way. Say an angle data is in standard position if its vertex is at the origin and its initial side lies along the positive x-axis. The terminal side is the ray where the angle ends. The terminal point is the point where the terminal side intersects with the unit circle. If data is in standard position, the terminal point is always cosine of data, sine data. The most common terminal points in different degrees and radians are 30 degrees, which in radians is pi over 6, but in terminal point it would be √3/2 and then 1/2. 45 degrees is √2/2, comma √2/2. 60 degrees is 1/2, √3/2. 90 is obviously 0, 1. And 120 degrees is -1/2, √3/2. 150 is -√3/2, 1/2. And 360 is 1, 0. And 270 is 0, -1. All right, now let's move on to inverse trigonometry. The first thing we're going to do is, can you get some of the notebook, please?
What?
Get some of the notebook.
All right.
Will be sine of x, or sine -1 of x. What you want to think about inverse trigonometry with sine and cosine, you want to think of the number 8. For sine inverse, think of sine being like the right side of the 8 coming down to the left side. So this is what it would look like on a graph. You can see the markings out a bit right here. It goes from pi/2 to -pi/2.
Shebang.
And then its domain would be -1 to 1, and its range would be -pi/2 to pi/2. Speak to cosine. Same domain, but for range it would be 0 to pi. It doesn't go past the x-axis. You can see it's the left part of an 8 going down to the right side of an 8, and it just looks like this. And this also can fit the horizontal line test and become a one-to-one function. For tan -1, range is -pi/2, pi/2, and that's parentheses. Sorry, that is a mistake. This is all parentheses for tangent, and the domain is -infinity to infinity. And this is what it would look like.
Most people see pre-calculus as just another math class.
A lot of formulas, a lot of graph, a lot of confusion.
But when you actually slow down, work through the problems step by step, math starts making more sense.
Today, we're breaking down 2 of the biggest units in pre-calc, higher power polynomials in trigonometry.
And instead of just giving answers, we're showing how the problems are actually solved. So stay tuned. Higher power polynomials. First, we'll start out with this formula. X cubed minus 4x squared minus 7x plus 10. The first thing we notice is that the highest exponent is 3. So this is a third degree polynomial, which is also called a cubic function. Our goal here is to find the roots. The roots are the x values where the graph crosses the x-axis, basically where the function equals 0. One strategy is testing possible values. This is sometimes called trial and error, or as we call it, brute force. Now, simply follow step by step. For this problem, you're going to plug 1 in for every x value that you see. 1 cubed minus 4 times 1 squared minus 7 times 1 plus 10. This would come out to 1 minus 4 minus 7 plus 10, which would be 0. So since the answer equals 0, this confirms that x equals 1 is a root. And by the factor theorem, if x equals 1 is a root, then x minus 1 is a factor. So if x equals 1 is a root, then x minus 1 is a factor.
Now we're going to use the factor of x minus 1 to find other factors in And to do that, we're going to use synthetic division. So we're going to use 1, which is our x equals 1, and then we're going to use the leading coefficient of these numbers, which will be 1, -4, -7, and 10. So first we want to just bring the 1 down. Multiply by 1, and then combine this, you get -3, and that, -3, -10, and that, -10, and then get you to 0. And so this proves that this is also a root, but it also simplifies our higher power polynomial. With this, you can take the leading coefficient and drop it down a power. So we're at x squared minus 3x minus 10. And now we can find the other roots.
Today I'm explaining the Arthur-Mensah signs as well, which helps predict how many positive and negative real roots a polynomial can have. Let's find the number of positive roots, take a look at the signs in f of x, and count how many times the signs change. For negative roots, plug in negative x and count how many times the sign changes in f of negative x. So for example, we use this formula right here. I can see the signs are positive, negative, negative, positive. Now let's look at f of negative x. Which would be -3. Sorry, negative x cubed, -4x squared. So 7x plus 10. As you can see here, the signs are negative, negative, positive, and positive. So as you can see here, there is one sign change, which is from the x cubed, which is from positive to a negative. So there is only one negative root. So using Descartes' rule of signs, we can predict either 2 or 0 positive roots and exactly 1 negative root.
Now we have to factor the quadratic. So here, we need two numbers that multiply to -10 and that add to -3. So what is the first number that comes to your mind that equals 10? Firstly, I think of 5 and 2. 5 and 2 works perfectly as well because there's a difference of 3. But since it is a -3, that means the larger number must be the negative. So here, it would be x minus 5, x plus 2. And don't forget, from earlier, x minus 1. So, now that we have to pull out all the x's, the value for x in each equals 5, 1, and -2. So those are the three factors.
Next is multiplicity. Example, x minus 2 squared. The exponent tells us the root repeats twice. Because the multiplicity is even, the graph touches the x-axis and bounces instead of crossing through. So take a parabola, for example. The parabola touches the x-axis and bounces back up instead of a linear graph that would just go through like that. End behavior depends on the degree and leading coefficient. Take -x2. The degree, -x3, sorry. The degree is odd, so the ends move in opposite directions, meaning instead of looking like this where the ends go in the same way, one would go in opposite ways with opposite arrows.
Polynomials are all about patterns and graphs and equations.
Trig takes those same ideas and applies them to angles, circles, and motion. Alright, I think we're all sick of polynomials, so now we have trigonometry basics. Let's start with angles. One important idea is coterminal angles. These are angles that end in the same exact position. Examples: 30 degrees, 390, and negative 330. Okay, 30. Say we have a graph like this. And imagine this being 90. So 30 would be right around here. You think, how could 390 equal 30 degrees? But imagine going around the graph 360 degrees. Oh, you're back at 30. So this is basically 390. And for negative angles, you want to think of, what if you just add 360 then to make it positive? Oops, you're back at 30 degrees. So this is also 30 degrees. And even if you want to go negative angles and just do it like that, you're in the back at this way. Because for negative angles, you want to go counterclockwise as opposed to the usual way that we count for angles.
Okay. However, the problem that is there is that trig problems are usually written in radians rather than degrees. To convert, we must multiply pi over 180. For example, 90 degrees equals pi over 180, which really equals 90 degrees means it's simplified to pi over 2. Because here it'd be 90 pi over 180, which simplifies down to pi over 2. Another answer.
Let's get into the big bad, the unit circle. Every point on the circle is written as x, comma, y. The unit circle has a radius of 1. The x coordinate represents cosine, the y represents sine. At pi over 2, you can just envision the point being 0, comma 1. So cosine pi over 2 would equal 0, and sine pi over 2 would be 1, since sine is y and cosine is x, resulting in y it's 0, comma 1. Now let's graph. So envision this: 2 sine of x. Let's write it down for you, and I'll show you the end result. The thing that differentiates sine and cosine is that sine the origin is at 0. Cosine, the origin is at 1. The number in front of sine is the amplitude. So you can just envision the amplitude reaches 2 units up and 2 units down. So it means it's 2 units up and it's 2 units down. The normal sine graph repeats every 2 pi. So start point and end point, like a wave, as a 2 pi. Since nothing changes inside the parentheses, the period stays at 2 pi, and the amplitude is 2, and the range becomes -2, 2. Let me just draw it out for you. You would have one thing I forgot to mention, you need the 5 holy tick marks. So you need 0, pi over 2, pi, 3 pi over 2, and 2 pi. The graph will reach 2, and at the lowest stage it will reach -2. It's going to start at 0, go up to 2, cross through pi, and then cross to 2 pi, and that's basically one single wave or one single period. This is what it would look like. This is the graph at the bottom right here. Man, I'm just struggling. This math stuff is getting to me. Look at my grades, 56. I don't get the Pythagorean identities, the inverse trig, and all the other stuff, the double angles. Teacher, could you help me, man?
Yep, sure thing. Here, I'll help you with one simple fact. Trig identities are equations that are always true. And the most important one that you need to know is sine squared of x plus cosine squared of x equals 1. And this comes directly from the unit circle in the Pythagorean theorem. One common identity is sine of 2x equals 2 sine x cosine x. So, for example, if we see the problem 2 sine x cosine x, or anything that simplifies to that, we know that it equals sine of 2x. Alright. Another useful formula is sine squared of x equals 1 minus cosine of 2x divided by 2. So 1 minus cosine 2x all over 2. And cosine squared of x equals 1 plus cosine 2x divided by 2. So, this also teaches us that tangent squared x equals to 1 minus cosine of 2x over 1 plus cosine of 2x. So, this is all the formulas that you need for all of your equations that you were struggling with. Let's get that grade up.
Thank you, teacher. This is going to help a lot.
Alright, let's use these topics my math teacher taught me to solve these problems. First problem is sine squared of x times cosine squared of x. You can do sine of x, cosine of x, and you can square it in parentheses. And what is sine of x and cosine of x? Simplified down to using the double sine angles. You get half sine of 2x squared, and sine squared of 2x simplify down to negative cosine of 4x plus 1 divided by 2. And remember, 1/2 squared is 1/4, so you have the 1/4 multiplying it. And that's going to get you negative cosine of 4x plus 1 divided by 8. Next problem. You have 2 sine of x divided by 2 times 3 cosine of x divided by 2. You can multiply the leading coefficients and get 6 sine of x divided by 2 times cosine x divided by 2. With this, you can use your double angle formulas that my math teacher taught me. You can do 3 times 2 sine of x divided by 2 cosine x divided by 2. And that inside the parentheses could simplify down to sine of x. And with the 3 multiplying it, you just get 3 sine of x. Third problem is cosine of 2x minus sine squared of x divided by cosine squared of x. Cosine 2x can simplify down to cosine squared of x minus sine squared of x. And you have the minus sine squared of x as the remainder from the non-simplified version of the equation, and then you have divided by cosine squared of x. That can simplify down to cosine squared of x minus 2 sine squared of x divided by cosine squared of x. You can split the fractions up into cosine squared of x divided by cosine squared of x minus 2 sine squared of x divided by cosine squared of x. And that will get you 1 minus 2 tan squared of x. Since the cosine squared of x is cancel out, and the 2 sine squared of x divided by the cosine squared of x gets you 2 tan of x, negative 2 tan of x, or negative 2 tan squared of x. For the last problem, we have cotangent of x minus tangent of x. You can split these up into their simpler forms. Cotangent cosine of x divided by sine of x, and you have tangent sine of x divided by cosine of x. You could square the numerators, which would just be the same version of the problem before, and you get cosine squared of x minus sine squared of x divided by sine of x times cosine of x. And as you can see, you can use the double angle formulas for the numerator and get cosine of 2x, and then you can use the double angle formula of sine to get half sine of 2x. And that would just give you 2 cotangent of 2x. The last problem is cosecant to the power 4 of x. First thing you want to do is change it to 1 over sine to the 4th power of x. From this you can change to 1 over sine squared of x squared. And that can just get you 1 over negative cosine of 2x plus 1 over 2 squared. When you multiply those together, you get cosine of 2x minus cosine of 2x squared minus 2 cosine of 2x plus 1 over 4. To get all the exponents out, you want to make it cosine of 4x plus 1 over 2 minus 2 cosine of 2x plus 1 over 4. To get the fraction out of the numerator, you multiply by 2, and that gets you cosine of 4x minus 4 cosine of 2x plus 3 over 8. And that's all over 1. Thank you, math teacher. I just got 100 out of 100 on my last test. Look,